Hello, Amsatters. I'm Nick, and I am a Cajun. I'm a tinkerer, I'm an engineer, I'm an educator, and I'm a huge fan of Bob Twigs. So I come from the Acadiana section of Louisiana. We call ourselves Cajuns. So you know you're a Cajun if you call the Four Seasons onions, celery, bell peppers, and garlic. You might be a Cajun if you let your black coffee sit and find it gel. You might be a Cajun if your favorite story starts with, first you make a roux. If you taste the five-alarm chili and say, pass the Tabasco, you might be a Cajun. If you refer to cool snap as gumbo weather, you might be a Cajun. And if you visit a zoo, you look for the recipe cards on how to cook it. But for you guys in here, most of you, I think, are tinkerers. So how do you know you're a tinker? Well, if you plugged yourself in the wall before you learned to walk, you're a tinkerer. If your ability to take things apart exceeded your ability to reassemble them, then you're a tinker. If you figured out what a flyback transformer was the hard way, and you silverhead guys in here probably done that, you're a tinkerer. If you built the crystal set, you're a tinkerer. If you built something that exploded and you innovated it, the process to make it bigger, you might be a tinkerer. If you got an FCC license, you're a ham and a tinkerer. So now what I'd like to do is I'd like to take the rest of this talk, tell you about what we're up to at the University of Louisiana. Let's talk about the mission. The mission is to give students the opportunity to design, build, launch, and operate satellites. Part of our mission is to light the spark that excited the likes of Tom Clark, Jan King, Bob Twigs, and other Amsat elders, and for the students to greatly enhance their ability to get scholarships and good jobs. So a brief history of what we've been doing at UL. Well, first of all, we got our first satellite launched in 07. The odd thing is, it's still up there. It's a little brain dead, though. In 13, we launched our second satellite, and it stayed up for about 11 months and can burn up. In January of this year, we got our third satellite on orbit, and it's still talking to us. Not too healthy, but we're working on it. And we propose to launch Cape 4 as soon as we can get it manifested for a launch. So what are we going to put up this time? Well, here on the left is a prototype of what we want to do. It's a 3U. And what's sort of unique about this 3U is that we also are going to try to launch 6 small satellites built by the middle and high schools in our area. And there's a picture of it on the right. So the mothership, the Cape 4 mothership, as we call it, of course, is a 3U. Its payload will include 6 small satellites. We're going to put a deep space radio in there. Our team wants to start to build satellites above LEO, so we're going to need a more enhanced radio. And so we call it our deep space radio. We're also going to put a rescue radio in there. We found that about half of all the Alana launches fail to communicate when they get on orbit. We're going to put in a radio that if everything on that satellite fails, this radio ought to come through and give us a back door. Our physics department wants to run a magnetic experiment, a neutron experiment. We're going to experiment with radiation shielding. This is in prep for our next Beyond LEO mission. And which is exciting is our physics guy thinks they know how to build a solar panel that gets 40% efficient. So we're going to fly it and tell them how it works. So let's talk about something new in our area. We're going to start 6 satellite clubs. These clubs will include middle and high school students in our area. We're going to ask them to launch at least 1 high-altitude balloon a year until we get manifested to fly. These clubs will be asked to construct a ground station to talk to their satellites at their school. We will ask those students to get licensed. And when manifested, we'll integrate their satellite for launch. And we want them to formally report to their student body their activities. So in our area, we are influenced by the Acadians and in the French language, and in French, T means petty or small. So we're going to call these things T-sets. That's a play on Bob Twiggs's thin sets. Now the dimensions of this thing are 3.5 by 3.5 by 1.25. Really big. We're going to include some solar panels on there, and if we're lucky, we're going to produce about a half watt hour per orbit. We're going to, of course, put a 18650 battery in there. We're going to run a shallow microcontroller. We're going to put a LoRa radio in there on VHF. We're going to have, of course, a deployable monopole. Our controller will be programmed in Arduino IDE, and it's manufactured by Arduino. And we're also going to put a 3.5 by 3.5 experimental board for the students to design their own experiments. The TSAT mission is to inspire middle and high school students to gain the skills to build, design, operate satellites in LEO, to prepare them for a rewarding technical career, to develop teachers in STEM. To accomplish their mission, they will have to acquire skills by working as a team, learning some C programming, orbital mechanics, electronics, mechanical skills, schematic capture. Let me do a pause here and tell you about schematic capture with our seniors at the college level. Then first they're making schematics. I'll walk into that lab and they'll start putting things on a pref board. By the time I get in there, it looks like a fuzzball full of wire, and they have no idea how to explain to me what they got, and makes it almost impossible for me to help them troubleshoot that thing. I've been threatening to grab a baseball bat and start mashing fingers on the lab table if they do that. And of course, we want these students to be leaders in their schools. So what can this little small TSAT do? Well, from a ground station at their school, we want them to communicate with their satellite and almost horizon to horizon. We want them to design experiments. And what could they do? Well, first of all, they can collect health data. They perhaps could develop an email or a tweet server. They can design sun sensors. They can put a 9-axis IMU on the satellite. But really, we want these students to use their imagination to design their own experiments. So what kind of experiments can they do? Well, of course, they can measure bus voltages and currents. They can measure the Earth's magnetic field. They can tell us about the rotation of the satellite. If they're really smart, they can generate a vector to the sun. They can measure the rotation. But again, we want to fire up their imagination to do anything they can dream up. And of course, we impose some pretty stiff power and space limits on them. So what's the life of this orbit? Well, you know, if we're really lucky, we might get a year out of that guy. What does it look like? Well, here's a prototype. You can see the solar panels. That's actually the solar panel board, which we now have in test. And what's inside that thing? Well, look, here are the major components down there. There's the frame of the solar panels. There's the radio. There's a shell controller. And there's the block diagram. And of course, we're going to put an experimental board in there. We expect them to generate their own experiments. So how will the students talk to their TSATs? Well, we're going to use one of these mighty fine, expensive LoRa radios. $6 at Spark Fun. A little bit more about that later. So how will it be powered? Well, we've talked about the solar panels. They're about 15% efficient. We're going to put a 18650 battery in there. How much energy will it capture? Well, if we're lucky, we're going to get about a half watt per orbit. And that's part of the challenges for the students. So now, what will the ground station look like? Well, for you guys that have had to deal with schools and how easy it is to get permission to penetrate walls and get coax up to the roof, we're going to try to do a little solving on that. So we're going to start with a J-pole, and we're going to put that on a non-pin mount. We're going to put the LoRa radio, an RPi-0W, and a battery in a box, and we're going to connect that to the cloud. And then they'll come back in their lab via the cloud and communicate that thing. And if they're really sharp and clever, they will convince their network administrator, aka a syscon, to punch a hole in their firewall, and they'll be able to play with that thing from their house. So let's talk about what's on the main satellite now. We're back to the deep space radio. So as our team wants to move out of LEO, we're going to come up with a radio that's got a system gain of 185 dB. It's going to have an output of plus 37. It's going to have a sensitivity of minus 148 dB. Now, guys, this is pretty dang phenomenal. The penalty we pay for that low data rate is 18 baud. But if our students are clever, we'll make that adaptive, so as the link budget improves, we'll increase the throughput. The DC input on this thing is 16 watts off an 8-volt bus, and when it's in low power, it's 33 millivolts, and when it's receiving, it's only and sleeping, it's only 10 microamps. Of course, the frequency, we're going to fly a VHF guy, but the radio can work from 70 to 1,000 megahertz. And of course, again, it has lower spread spectrum, chirp spread spectrum. So what's in the deep space radio? Well, first of all, it's a tech demonstrator with a very sensitive radio. Of course, it uses the lower format. It'll have a system gain of 184 dBm on VHF. And if you put a 14 dB Yagi on the ground, we will kick that system gain up to 198. So what's inside this thing? Well, we're going to have 2 voltage rails, 3.3 and an 8-volt rail. We're going to talk to it on an SPI bus and a GPIO bus to control the amplifier and the switches. And again, this thing will be minus 148 dBm sensitivity with a power output of 37 dBm or 4 watts. So what can you do with that thing? Well, if you added a 10 watts on the ground and a Yagi, you can command that spacecraft out to about 1 million miles. And if you only had 1 watt on your ground station, that make it easy to communicate in geosync orbit. Of course, again, we do this at a really low data rate of 18 baud. Now, our rescue radio, we've noticed that most of the Alana satellites, half the satellites fail to communicate on orbit. This thing will work from 70 to 1,000 megahertz. It'll have a system gain of 168 dBm. Again, it's chirp modulation. We'll have a data rate from 18 baud to 125 kilobits. And the power output when it's sleeping is 2 microwatts, and when it's transmitting, it's 33. And when it's receiving, it's 33. When it's transmitting, it's at 300. Again, it'll use a Shao microcontroller, and the interface to the rest of the world will be UART, I2C, GPIO, SPI. So quickly, what are the outcomes for the kids? Well, they'll learn about orbital mechanics. They'll be learn to communicate to objects out to 2,000 miles, proficient in C, master collaborations, working in a team. They got to learn to deal with very small power sources. They got to be proficient in electronic and printed circuit design. What's the outcome for Amsat? This is where we're going to get our next designers. So guys, this is my story. We invite you to come see us. We want you to enjoy our fine food. We want you to listen to some of our Cajun Zydeco music. We want you to come help us. We want you to have fun. And I'll take questions.